We're continuing with Chapter 2 in the calculus textbook. Again, Chapter 2 is really the opening chapter of the subject of calculus in this textbook, being that Chapter 1 is more of a pre-calculus. And so we're starting in Chapter 2, starting in calculus, learning all about limits, because limits are the foundation of all of calculus. And in the opening two sections of Chapter 2, we really developed a highly intuitive understanding of what limits are. And we also developed a sense for how to evaluate limits as well. We developed this sense mainly by working a bunch of graphical limit problems, evaluating limits graphically. Okay, but as we talked about, actual limit problems that we're most familiar with when it comes to solving limits are like shown here. So this is specifically a single variable limit problem. We could do limits with multivariable functions, but in general, in calculus, single variable calculus, calculus 1, calculus 2, this is typically what we think of, something like this, when we think of a limit problem. The limit as x approaches a number, or perhaps plus or minus infinity, of some expression of x, some function of x. Okay, and so with the understanding of limits that we developed in the first two sections, we have an intuitive sense for what this means, right? Because an expression of x like this, a function of x like this, is just a graph, right? We can absolutely graph this, and we have a lot of practice doing graphical limits. So, I mean, we could just go look at the graph of x plus 2 over x cubed plus 8 around the x value minus 2 and just do a graphical limit problem, right? And I mean, actually, we could do that. That's one way to solve limit problems. Absolutely. If you're trying to solve a limit problem, it's very helpful to go to a graphing software and get the graph of the function you're dealing with. Absolutely. Okay, but we also want to be able to solve a limit problem like this just purely mechanically, or at least, even if we're going to pull up the graph of the corresponding function of the limit, we still want to be able to have a very solid feel for how to work with the problem from a purely mechanical standpoint. So without using a graph, just using the expression. We want to understand limits from a mechanical, algebraic, numerical perspective without having to always use the graph. Okay, and that's the main purpose of section 2.3, calculating limits using the limit laws. In this section, we're learning how to evaluate limits mechanically. Okay, so it says in section 2.2, the previous section, we used calculators and graphs to guess the values of limits. But we saw that such methods don't always lead to the correct answer. Yeah, so we saw in the previous section that there was many examples. That was one of the main points of the previous section, that just using a calculator and plugging in values closer and closer and closer to the limit point, the point that the input is approaching, didn't always lead to the correct answer. And now they mention that neither did doing limits graphically always lead to the correct answer either. And what they're talking about there is, so if we look at one of the graphical limit problems that we worked, okay, here's the graph of this function f of x. So for these problems, if you think about it, we're inherently making certain assumptions when solving a problem like this. Like, okay, for the limit as x approaches 2 of this f of x here, we're assuming that the function is defined that we could get infinitely close to 2. Let's say the limit as x approaches 2 from the left. We could plug in 1.999, a trillion nines, a quintillion nines, and we're going to get some value that's just above 4.000, a trillion zeros 1. But we don't know for sure if that's the case, right? I mean, we'd have to check. We need to zoom in on this graph. If we zoomed in really close to where the axes were, just on the screen, you were going from 1.999, 100 nines, to 2.000, 100 zeros 1, then maybe we would see that the graph does something different. Maybe it's oscillating. We just can't see it. We're zoomed out too much, right? And so if we were really nitpicking and wanted to make an 100% precise statement about these limit values, even though that wasn't the point of these problems, this was just like an exercise. But if we were having to make like a statement that would hold up in court about the limits of these functions, we would have to state for sure that make a statement about how this limit behaves going all the way up to the point, which we could do with an expression of x, like the definition of a function as an expression of x. Okay, and so that's what the textbook is really talking about. And that evaluating a limit just using a calculator or graphically isn't an in general bulletproof method for evaluating limits. So if we're dealing with a limit from the perspective of its actual expression of x, then we can use these properties of limits listed here, called the limit laws, to evaluate the limit. Okay, and so again, just using calculators and graphs to guess values of limits, it's not foolproof. It's not bulletproof. You might not always get the correct answer. So in this section, we use the following properties of limits called the limit laws to calculate limits using the actual function itself, the function expression that you're working with. The limit as an input approaches some value of some expression of the input. Okay, so we've got, this first property here, the limit as x approaches some number a of a function x plus another function x, you can sort of distribute the limit. So this is equal to the limit as x approaches a of f of x plus the limit as x approaches a of g of x. Okay, and then you could do the same thing with the subtraction of the limit of the subtraction of two functions. Here in these last two rules, it shows that you can distribute a limit even if you're multiplying two functions. Then you can just distribute the limit to each of the individual functions and multiply the two limits. And same idea with division. Okay, but now note how it says that these rules are only valid if the limit as x approaches a of f of x and g of x exist. Otherwise, these rules aren't valid. Okay, and with that, also note how in an infinite limit, so a limit to where the function approaches positive or negative infinity, so that the limit itself, the limit as x approaches a of f of x is equal to positive or negative infinity, would be an infinite limit, right? Well, remember, infinite limits technically don't exist. Yes, we can put the infinity symbol as the answer, but those limits don't exist. So like, for example, rule 1, if you found that the limit as x approaches a of f of x is equal to infinity, and the limit as x approaches a of g of x is equal to 22, well, then you can't say that this is equal to infinity plus 22. No, because this limit doesn't exist. So the whole rule doesn't apply. I mean, in a case like this, we could still sort of abstractly apply this rule, but we'll talk more about limits like this, that these are called indeterminate forms of limits in chapter 4. But for now, we're only thinking about these rules, these laws, for the cases where all limits involved exist. And therefore, as we know, if a limit exists, then that means that the limit evaluates to a single, unique, distinct number. Okay, and also note that this last rule here, so just like the other rules, that this doesn't apply if either of the limits of f of x or g of x don't exist, but this also doesn't apply if for any case where the limit as x approaches a of g of x does exist, but it's equal to 0. Because in that case, you'll be dividing by 0, so then this doesn't evaluate to anything. Okay, but one thing I want to point out about these laws is that if you think about it, they're very intuitive. Also, these laws also show how limits are very flexible. Like, so we can see for any addition, subtraction, multiplication, or division of two functions of x, you can just easily distribute the limits to the different expressions, right? A lot of properties we see in math, they'll apply for the sums of objects like this, but they don't apply for, if you're multiplying or dividing objects. But this is really flexible. If you're adding or subtracting expressions, multiplying, dividing, you can just distribute the limit to each expression. Or here you could just take out any constants out of the limit. And that's really nice, right? But if we think about it, it's really intuitive why this is the case, why limits are so flexible like this. It's intuitive to understand where these laws are coming from. And once you get a feel for how flexible limits are in relation to expressions of x, it will make you a lot more comfortable when dealing with any limit problem. Because, okay, once again, let's assume that whatever limit we're dealing with does exist. And so with that in mind, what you can think about is you could imagine a nasty complex expression of x that's the argument within a limit. Let me give you an example. So a limit like this, really complicated expression of x as the limit argument, right? But, okay, we can look at this from a simplified perspective, in that you can think about how we can put a box around whatever region of x values we want. So you could put a box here, and here, and here, and here. And what's nice about this is, if you think about it, we could pull all of these x expressions out of the limit and analyze what each of these expressions does as x approaches a individually. We could say, okay, what's the limit as x approaches a? What is this expression doing? And what's this expression doing? And this expression. Right? So we could analyze all of these individually, right? And so it should make sense to you why we could analyze any region of a limit in its own box. Because whatever x is approaching, we're just trying to figure out, okay, so what is this doing? And if the limit exists, then all of anything you box in is going to have to be approaching something, some finite unique value. If the overall limit exists, that's going to have to be the case. And so you can figure out, so what's this approaching? You can think about this, that this really makes sense if you go back to the whole hypothetical enormous calculator thought exercise. So if you had an enormous calculator and you plugged in x extremely close to a, okay, what is this doing? This is going to be approaching, let's say, L1. And this, if you analyze this, this is approaching L2, and this L3, and this L4. Well then, okay, to evaluate what this entire expression is doing as x approaches a, you just replace this with L1, and this with L2, this with L3, this with L4. Divide these two numbers, e to the square root of this number, sine of this number, take the log of that. That's what the whole limit is approaching. You see? You see how that works? You see how that makes sense? And so that should give you some intuition as far as where these rules come from. It's easy to just distribute the outer limit of any limit expression to the inner expressions. Okay, but now what we just went through here with this complicated logarithm limit wasn't in conjunction with any of the rules here, right? We don't see any logarithms or roots, etc. So for the moment, let's just follow along with the book and assume that these are all of the rules we know of regarding limits. As we get further into this section, and also mainly with a theorem we're going to learn in section 2.5, we'll see how we are officially able to distribute an outer limit anywhere we want into a complicated limit expression like this. Okay, so it says, it is easy to believe that these properties are true. Exactly, they're very intuitive. For instance, if f of x is close to L and g of x is close to m, then it is reasonable to conclude that f of x plus g of x is close to L plus m. Exactly. This gives us an intuitive basis for believing that law 1 is true, and then you could do the same thing for all the other laws. In section 2.4, we give a precise definition of a limit and use it to prove this law. The proofs of the remaining laws are given in the appendix. Okay, so let's use the limit laws in the graphs of f and g to evaluate the following limits if they exist. So what is the limit as x approaches minus 2 of f of x plus 5 times g of x? So all we're needing to do is, we could apply the whole sum rule and the constant multiplier rule where we could bring this out of the limit, but we could just think about how, so as x approaches minus 2, here's minus 2, f of x is approaching 1/2, and g of x is approaching, or no, minus 2 is here. So f of x is approaching 1, and g of x is approaching minus 1. So we can really just do this, right? So this limit is going to be equal to 1 minus 5, minus 4. Okay, as x approaches 1 of f of x times g of x, we've got the limit of x approaches 1 of f of x is 2, g of x it doesn't exist. Okay, wait, no. Or this limit doesn't even exist in general, 1 in general. The limit as x approaches 1 of g of x doesn't exist, so this entire limit can't exist, right? This is D and E. It doesn't matter that the limit as x approaches 1 of f of x is 2. So this whole limit doesn't exist. Okay, the limit as x approaches 2 of f of x is about 1.4, and g of x is 0. Okay, so we could do 1.40, but you can't divide by 0. So this limit doesn't exist. Okay, so if we use the product law repeatedly with g of x is equal to f of x, we obtain the following law. So what they're saying here is you've got the limit as x approaches a of f of x to the n power, so it's like all of this is within the limit, then you can take that n power and bring it outside of the limit. You just do the limit as x approaches a of f of x to the n. And this makes intuitive sense, right? We could really intuitively have figured this out on our own because, again, limits are so flexible. But they're trying to prove all these properties rigorously from a math perspective, right? Because in effect, the fact that we brought this in outside of the limit, this exponent, if we come back here, what we did here was we brought like the log outside of the limit, right? We said the log of this limit is equal to the log of the limit as x approaches a of everything inside of the log. But then we went even further. We started bringing distributing the limit to each of these individual expressions. Limits are very flexible, okay? But again, they're going step by step here, trying to mathematically prove everything. You can't just make statements in math purely based on intuition. So what they're doing here is they're saying, look, if for this property, if we say f of x is equal to g of x, then you've got the limit as x approaches a of f of x squared. But then you could keep doing that however many times you want to get the limit as x approaches a of f of x to the n. But then you could break all of those up, right? The limit as x approaches a of f of x times the limit as x approaches a of f of x times the limit as x approaches a of f of x. And then what you have is you've brought the n power outside of the limit. And that's what they're showing here. But they're saying, for the moment, we're just thinking about n as a positive integer. Because if n is a negative integer, now we're taking a reciprocal of a function. So no, just at the moment, n is a positive integer. You're multiplying f of x, is the limit as x approaches a of f of x multiplied by itself n times. In that case, you can simplify this by taking that n power outside of the limit and saying this is equal to the limit as x approaches a of f of x to the power n. Okay, now in applying these 6 limit laws, we need to use 2 special limits. So the limit as x approaches a of c is equal to c, and the limit as x approaches a of x is equal to a. These limits are obvious from an intuitive point of view. If to state them in words or draw the graphs of y is equal to c and y is equal to x. But proofs based on the precise definition are required in the exercises for section 2.4. So yeah, they'll go through official proofs of these, but intuitively, in particular, if we think about the graphs of y is equal to c and y is equal to x, these make sense. Okay, now if we put f of x is equal to x into law 6 and use law 8, we get another useful special limit. So you take f of x is equal to x in law 6. If f of x is equal to x, and then use law 8. So because what you're going to get is the limit as x approaches a of x to the n. You can simplify that as, because f of x is equal to x, the limit as x approaches a of x, all of that to the n. Well, then the limit as x approaches a of x is equal to a, right? So you're left with a to the n, where once again n is a positive integer. Okay, now it says a similar limit holds true for roots as follows. The limit as x approaches a of the nth root of x is equal to the nth root of a. So here we were saying the limit as x approaches a of x to the n is equal to a to the n. Here we've got the limit as x approaches a of the nth root of x is equal to the nth root of a. Okay, they don't prove this right here, but you can think about how we could write this as the limit as x approaches a of x to the 1 over n is equal to a to the 1 over n, right? But then you could easily combine this rule with rule 9, which is based on powers of x and the general properties of rational exponents, to say that the limit as x approaches a of x to the m over n is equal to a to the m over n, right? Because the m is just the exponent power component of the m over n rational exponent. Okay, so it says that the denominator here, the root, is a positive integer, and that's true. We don't think about roots, indexes of roots that aren't positive integers. And then it says if n is even, then we assume that a is greater than 0. And that's because we're only talking about real numbers, and we aren't thinking about taking an even root of a negative number. Now you might say, why can't a be equal to 0? We can take an even root of 0, can't we? Well, yes, but remember, this is the limit as x approaches a in general, which means we have to approach a from both sides. And so if a was 0, we couldn't approach a from below. As a one-sided limit, so the limit as x approaches a from above, we could say in that case that this law holds with a being greater than or equal to 0. Okay, but now in the next rule, they just extend rule 6 in the same way that rule 9 was extended, to where rule 6 applies with exponents of 1 over n. So the limit as x approaches a of not x, but of any general function f of x. The limit as x approaches a of the nth root of f of x, you can take that nth root out of the limit. But you could think about how, once again, in conjunction with rule 6, the corresponding power rule of this, the limit as x approaches a of f of x to some positive integer power is equal to, and then you could take that power out of the limit. You could easily show that, for any general root, the limit as x approaches a of f of x to the m over n power, you can take this looks like a one-sided limit. That's not what it is. There we go. You could take that power out of the limit. Okay, so now we've got a few extra laws in addition to the original 6 laws. So if we take a look at this next example, so part A, the limit as x approaches 5 of this this polynomial expression here, this quadratic expression, quadratic function. Okay, now this time, unlike this first example we worked where we were referencing the graph, this time for these two examples, we don't have a graph to reference. I mean, we could use a graphing software to graph these functions, but let's think about this purely mechanically. So they start, for part A, they start by using the sum rule to distribute the limit to each term. Then they use the constant multiplier rule to bring these constants out of these two limits. Okay, now all of these remaining limits apply to the properties we just discussed. So the limit as x approaches a of x squared is equal to a squared. So this is 5 squared. The limit as x approaches a of a is equal to a. Here the limit as x approaches c of, or the limit as x approaches a of c is equal to c. Right, that was this. The limit as x approaches a of c is equal to c. So they evaluate the limits, simplify the expression, and get 39. And now for part B, they start by just using the quotient rule. That would be rule, they don't call it the quotient rule, but it rule 6 here. And they distribute the limit to the numerator and denominator. Then go through so like here, then they just go through the same process as what we just did in part A for the numerator and denominator. And they get minus 1 over 11. Okay, but now here it says to note how for each of these limit problems we just did, we could have just plugged the limit value into the expression. And then the result of the expression is the limit, right? If you noticed for either of these limits, we could have just taken 5 here and just plugged it straight into this expression. 2 times 5 squared minus 3 times 5 plus 4 is equal to 39. Same here. We could just plug minus 2 straight into this expression and gotten the answer to the limit. Okay, and so it says the functions in example 2, the two problems we just worked, are a polynomial and a rational function respectively, and similar use of the limit laws proves that direct substitution always works for such functions. Okay, so with that, they state the following property, the direct substitution property. If a function is a polynomial or a rational function and a is in the domain of f, then the limit as x approaches a of f of x is equal to f of a. Okay, so this property is saying that if you're evaluating a limit to where the expression in the limit is a polynomial or rational function, reminder, a rational function or rational expression is a ratio of polynomials, then if the limit input value a that's being specified for x to be approaching is in the domain of the expression, which just means that if you plug that value into the expression, you get an output. So like you're not dividing by 0 or something, then the limit itself is equal to the value that you get by plugging the input value into the expression. So like it says here, f of a. Okay, then, so does that mean if we had a limit to where the function was a rational expression, if we plugged in the limit point into the expression and the result was dividing by 0, we got a 0 in the denominator, does that mean that the limit in general, the main limit, doesn't exist as well? No, that's not what they're saying here. All they're saying is that if it is the case that the limit function is a polynomial or rational expression, which is f of x, and at the same time the limit point a, the value that the limit is specified to be approaching, happens to be a value that is in the domain of the expression, then in that case the overall limit expression is equal to f of a, the function evaluated at a. However, if the limit point a is not in the domain of f of x, then you'll have to analyze the limit further to determine if that limit exists or not, and if it does exist, then what is the limit? Okay, so where is this rule coming from? Why does this only apply to polynomial and rational expressions? Well, if we come here, it says functions with the direct substitution property are called continuous at a, and will be studied in section 2.5. So once we learn about the precise meaning of continuity in section 2.5, we'll see how the direct substitution property doesn't apply. It's not really about polynomial or rational expressions, but it's more about continuous functions. Because polynomial and rational expressions are continuous everywhere in their domains, then they apply to this direct substitution property. Okay, we talked about continuous functions briefly in algebra, and an informal but very useful way of thinking about what a continuous function is it's any function to where you can draw that function without picking up your pen off the page. So really, you could say that an entire function is continuous. Like, for example, all polynomials, any polynomial is going to be continuous for their entire domains, which is all real numbers. So the idea is you could start at negative infinity, and for any polynomial, you could draw that polynomial all the way to positive infinity without ever picking up your pen off the page. Okay, but you don't have to state that just like an entire function is continuous or not continuous. You really think about continuity from as specified by intervals. So you'll say a certain interval of a function is continuous or not continuous. So with rational functions, in most cases with any rational function, you're going to have some region of that function, at least one region, that's to where you're dividing by zero. You have a vertical asymptote. And so when drawing a rational function and crossing over a vertical asymptote, you're going to have to pick up your pen off the page, right? No matter what, because you can't have your pen cross over a point where the function doesn't exist. So the rational function is not going to be continuous at that point. But still, you could state something like this rational function here from x is equal to this minus 5 to 3 is continuous because over this entire interval, you can draw the function without picking up your pen off the page. And if you think about it, that's where the statement that, so obviously polynomial functions are continuous everywhere, no matter what, but we stated how polynomial and rational functions are continuous everywhere within their domains. And what that means is that as long as you're in the domain of the function is continuous. As opposed to something like this, okay, well, crossing over 2, we never leave the domain of the function, right? X is with the rational functions at the discontinuities, you're outside the domain of the function. Well, this f of 2 is in the domain of the function. F of 2 is equal to 3. Okay, but still, even though this is in the domain of the function, you can't draw this, cross over this point without picking up your pen off the page. Okay, and a similar idea here, but x is equal to 4 is outside of the domain of the function. The function doesn't exist at 4, but we could put something like this. Now f of 4 is in the domain of the function, but we still can't draw this without picking up our pen off the page. So it's a discontinuity, right? And so with that, you can think about how the statement that rational functions and polynomials are continuous at all points within their domain. Okay, and so with this informal definition of continuity, you can see how it makes sense if you're thinking about the limit of a function as x approaches a value that's within the domain of the function, and the function is continuous at all points within its domain, then the limit is just going to be equal to the function itself evaluated at that point. Right? Because think about some of the graphical limit problems that we worked. Sometimes we were just given, so like the limit as x approaches, and they would say like something like 5 of f of x is equal to what? So just some point on the curve that didn't have any, there was no kind of like discontinuity or a hole or anything. It was just like a just random point on the general curve, like this. What's the limit as x approaches 5 of f of x? Okay, well, this is almost trivial because you're coming from both sides. Obviously, the function is approaching the same value, and that value being whatever the function is equal to at that x point, the x point of interest, the point you're approaching, f of 5. Okay, so that's where this direct substitution rule is coming from. And again, once we learn the official meaning of continuity in section 2.5, we'll be able to make the overall general statement of how the limit of any function as the input approaches a value of which the function is continuous at is equal to the limit function evaluated at that value. Okay, but now it says, however, not all limits can be evaluated by direct substitution, as the following examples show. So, okay, this example 3 gives the limit as x approaches 1 of x squared minus 1 over x minus 1. So this is a rational function, a ratio of polynomials, right? Okay, so why don't we just go ahead and, based on the direct substitution property we just learned, plug in 1 into this expression. And we get a 0 in the denominator. We can't divide by 0. So the direct substitution property doesn't apply here. Now, we did look at an example problem in the previous section to where a limit like this, where you have a denominator present and the denominator is approaching 0, this could be an infinite limit, right? Because if you're dividing a number by a tinier and tinier and tinier number, then the output would be ballooning to an infinitely large positive or negative number in magnitude. Okay, but the only way that this happens is if, so you have to have the denominator approaching 0, but you also have to have the numerator at the same time approaching a finite value or values other than 0. So again, the denominator needs to obviously be approaching 0 in order for the output value to be ballooning to positive or negative infinity, but you can't also at the same time have the numerator ballooning to positive or negative infinity or approaching 0. A form of a limit like this, so an infinity over infinity, or a 0 over 0 form, infinity over 0 form, etc., are what's called indeterminate forms of limits. Well, actually, if you had like an infinity over a 0, the numerator is approaching infinity, denominator approaching 0, then that actually you could state that would be infinity. But I don't want to get too far ahead of ourselves here. Okay, indeterminate forms of limits, which we can see that this is an indeterminate form because the denominator is approaching 0, but so is the numerator. As x approaches 1, in general, the numerator is getting closer and closer to 0, just like the denominator. So we can't make a statement about, oh, well, we're dividing by a tiny number so that the output is ballooning. Well, okay, no, because, well, how tiny is the denominator number relative to the numerator number? It's indeterminate. Okay, and so we'll talk in detail about indeterminate forms in chapter 4. Okay, and so for this limit, we can't apply the direct substitution property for rational functions, and we can't look at this as just a general infinite limit like we saw in the previous section. Okay, but in this case here, we don't need to use any special techniques to deal with this limit like what we'll learn in chapter 4 when dealing with indeterminate forms. Because in this case, we have the ability to simplify this algebraic expression. And that's really the first step when solving any limit problem mechanically. Or it actually would be the second step, because the first step would be to check if a direct substitution is applicable. And then if it is, just plug the limit point into the expression. But the second step would be to simplify the algebraic expression as much as possible. And here, if you noticed, we can factor the numerator as x minus 1 times x plus 1, and now the denominator is x minus 1, and we can cancel the x minus 1s to where the limit becomes the limit as x approaches 1 of x plus 1. And then from there, what they do is They say that, well, this is just a polynomial, right? It's the equation of a line, which is a polynomial. With that, we can apply the direct substitution property. Plug in x is equal to 1. 1 plus 1 is 2. So that's the answer to the original limit. Okay, but now you might say, well, wait a minute, hold up. How could we apply the direct substitution property right there? Like, yes, x plus 1 is a polynomial, but this is a unique case in that it's really technically not a polynomial because it comes from the original rational expression, right? This x plus 1 is a simplified form of this. And we know from algebra, so if we were to if we were going to graph this, then all this means when we simplify. So we're going to make this graph, but we simplify and get this. What that's telling us is that, okay, this is actually the equivalent to x plus 1. The graphs, these two graphs are going to be the same. The only difference is that we can't plug in x is equal to 1 into this function. Like, yes, we can here, but this is tied to this. So the graph, what this is telling us is that the graph of this is the line x plus 1, the actual line x plus 1 with slope 1 and y-intercept 1, with the only difference being we're going to put a hole at x is equal to 1 in that line because we can't obviously x is equal to 1 is not on this graph. You can't divide by 0. And so from that perspective, you're wondering, okay, well, wait a minute, like the direct substitution property was all about how polynomials are continuous everywhere in their domains. Well, this x plus 1 here is not continuous everywhere in its domain. It's tied to the graph of this x plus 1 has a hole in it. So we can't just, how can we just apply the direct substitution property here? Well, okay, that's true. That's true. But for a case like this, we were able to apply direct substitution to this simplified form, no problem, because the only aspect that was affected with respect to the original function, the only difference between this x plus 1, the literal graph of the line, the actual line y is equal to x plus 1, and the literal graph of x squared minus 1 over x minus 1, the only difference was in relation to what was occurring at the actual limit value. Everything else was equivalent, right? The only difference between x squared minus 1 over x minus 1 and x plus 1, completely, like if they're independent, is what the function is doing at the value x is equal to 1, which is the limit value here. Well, okay, but we know that one of the big ideas about limits is that when evaluating limits is that we're not concerned with what's happening at the limit point itself at all. And so because of that, we can just evaluate this limit here as if we were dealing with the actual line x plus 1 with no holes in it. In that case, then the direct substitution property applies. And they state this whole idea here with this property. They're saying that if f of x is equal to g of x, if you have two functions that are the same, they're exactly the same except when x is equal to a. So, okay, they're exactly the same when x is not equal to a. But at x is equal to a, they could be different in whatever way. If that's the case, then the limit as x approaches a of f of x is equal to the limit as x approaches a of g of x, provided the limits exist. And this is completely intuitive. The whole result of this is because what's happening at limit, the actual limit value itself, the limit point, what the function is doing is completely meaningless when it comes to limits. So this makes complete intuitive sense. Okay, now this next example says find the limit as x approaches 1 of g of x, where here's g of x. G of x is equal to x plus 1, where x is not equal to 1, and pi when x is equal to 1. And so, yeah, I mean, we could do this graphically. Here's the graph and do a graphical limit, but let's try and think about this with these limit laws mechanically. Okay, they're illustrating this property here. This example is illustrating this property. They're saying that, look, we've got some function here that is, they're saying is, the function is x plus 1 everywhere where x is not equal to 1, but something else when x is equal to 1, and we're dealing with a limit of this function as x approaches 1, well, we don't care about this. This could be equal to a leprechaun here, like we talked about before, right? Like what's happening at the limit value doesn't matter. So we can then, just to make things easier, let's just take the limit as x approaches 1 of just x plus 1 in general, the actual continuous, fully continuous line, polynomial x plus 1. That's going to be equal to this limit. And okay, now the direct substitution property applies. Just plug in 1. You see? Okay, here, evaluate the limit as h approaches 0 of 3 plus h squared minus 9 over h. And so, okay, we have a rational expression here, right? A ratio of polynomials. We plug in 0, but we're dividing by 0, so we can't use the direct substitution property. And so the next step is always going to be to see if you can simplify the expression. And so we've got let's see, we have a difference of squares here, but what they do is they distribute the 3 plus h squared and then combine the 9 into the expression and get, the 9's subtract out, so then you're able to factor out an h and cancel out these two h's and get 6 plus h. So this is equal to 6 plus h. But this function, the graph is the line 6 plus h, or h plus 6, with a hole in it at h is equal to 0. Okay, but again, we don't care what's happening at the limit value itself, so we can actually literally state this limit as this is equal to the limit as h plus 0 of h plus 6, the actual line itself, with no holes in it. And so the direct substitution property applies, and you get the limit is equal to 6. Okay, now this next example, find the limit as t approaches 0 of the square root of t squared plus 9 minus 3 over t squared. It says we can't apply the quotient law immediately. Yeah, so I mean, I guess that would be another initial step you would go through. So you try the direct substitution property. If that doesn't work, then if you're dealing with a quotient like this, then you could consider distributing the limit to the numerator and denominator. But you can see how for all the problems we worked, that when you do that, the limit of the denominator is going to be 0, right? Limit as t approaches 0 of t squared of h of x minus 1, that limit is 0. But yeah, so you could be given a limit and you try direct substitution. If that doesn't work, then you could think about applying any of the properties we've learned, any of these properties. Okay, but then from there, if you're stuck, then the next step is going to be to simplify the f of x, the expression, as much as possible, and go from there, right? And that's what we've been doing in these last two examples. Okay, and we're going to do something similar here. Okay, so something else you want to keep in mind is if you're ever looking at a limit problem and you've got it's a ratio like this, and in the numerator or denominator there's a radical, then you want to consider rationalizing that radical, which is to rationalize. What you're thinking about is you're going to be multiplying by the conjugate of the expression involving that radical. The majority of the time, if you're dealing with a limit problem that it's a ratio, and in the numerator or denominator there's a radical, and you're unable to solve that problem with a direct substitution, some simple method, and so you can need to think about algebraically manipulating the expression, then the large majority of the time, what you're going to need to do is rationalize that radical by multiplying by the conjugate of that radical expression. So multiplying this expression by 1 in the form of the square root of t squared plus 9 plus 3 over the square root of t squared plus 9 plus 3. And that's what they do here. So they're not changing the expression, right? This is just a form of 1. So they distribute this, and it ends up, because these are conjugates, the radical goes away in the numerator, and so they simplify everything, and the result is they get to here, and then they can cancel out the t squares, and you get a more simplified form of the expression here. Okay, but now you might say, okay, well, let's do direct substitution then, right? And yeah, you could do that, but technically we haven't stated any official rules that will allow us to do direct substitution. So like, yeah, we'll learn later how this would apply to direct substitution, but as of now, this isn't a rational expression, right? This isn't a polynomial in the denominator. In the numerator it is, but not the denominator. So we can't really do direct substitution, but we can use the limit law where we distribute the limits to the numerator and denominator. Well, this limit is 1. Limit as t approaches 0 of 1 is 1. And here we can apply the sum rule to where to the denominator expression, and then apply the root rule, right? The limit as x approaches a of the nth root of f of x is equal to, you could take that root out of the limit. And now we've got a polynomial, the limit of a polynomial, and so direct substitution applies there, and there we go. The limit is equal to 1/6. And now remember, don't get bogged down with thinking about, well, okay, we got to this simplified expression here, okay, this function 1 over the square root of t squared plus 9 plus 3, but it's not like you could just go into Desmos and graph this, and that's the graph of this function. No, because this function came from here, right? This function, there's a hole in this at t is equal to 0, technically. Well, who cares? We're evaluating the limit at t equals 0. We can just act like this is the function we're dealing with, where there is no hole at t equals 0. You see? Okay. Now, it says some limits are best calculated by first finding the left and right hand limits. The following theorem is a reminder of what we discovered in section 2.2. It says that a two-sided limit exists if and only if both of the one-sided limits exist and are equal. Yeah, we talked about this in the previous section, that the limit as x approaches a in general of a function is equal to L only if the corresponding one-sided limits are both equal to L, right? That's a requirement of a general limit approaching a value from both sides. And saying that, sometimes it's best to determine a limit by calculating each of the one-sided limits, seeing what the one-sided limits are, and then showing, okay, they're the same, so that means that the limit in general is equal to that value, like they're showing here. So, okay, show that the limit as x approaches 0 of the absolute value of x is equal to 0. So here's you have an absolute value function of just x. You have like a kink right here, because at the crossover point, it's just like it's not smooth. It just all of a sudden changes direction, right? Now, this is the absolute value of x is a continuous function. You can draw this entire function without picking up your pen off the page. And so we are going to see that since this is continuous, we could just plug 0 in here. We're going to see how direct substitution is applicable for any function that you're evaluating a limit at a point where the function is continuous. But we technically haven't learned that yet. We only can apply direct substitution right now if we're dealing with a rational expression or polynomial, and that's not what absolute value of x is. So what do? Well, what we can do is we can say, okay, let's write we know the definition of the absolute value. It's a two-part definition to where it's the line y is equal to x when x is greater than or equal to 0, and the line y is equal to minus x when x is less than 0. That's exactly what the absolute value is. Okay, and so we can say, all right, well, what's the limit as x approaches 0 coming from the right of this function? Well, in that case, we're just dealing with a polynomial, right? We don't have that. We got rid of the absolute value. That's just the limit as x approaches 0 coming from the right. Now we can take away the absolute value, and we can use a direct plug-in here, because we're just dealing with the y is equal to x. We get 0. And then similar idea coming from the right. So now, since the left-hand and right-hand limits are both the same, we can state that the limit as x approaches 0 of the absolute value of x in general is equal to 0. Okay, now this next example says, prove that the limit as x approaches 0 of the absolute value of x over x does not exist. So once again, we can break this down into like a two-part limit, because we can break up this definition of the absolute value as far as, so as x approaches, we're at the crossover point here of the absolute value. If we imagine that if we weren't, let's say we weren't at the crossover point of the absolute value, if this was the limit as x approaches 2 of this, then what would we do? Well, we can then say, well, look, well, we're only thinking about when x is approaching 2, very near 2, from above and below positive 2. Well, this is always positive. Absolute value of x is always positive there. So we could just remove the absolute value. You see? Well, here we're at the crossover point, so we have to break this down into, okay, if we're approaching 0 from the right, then we just remove the absolute value. If we're approaching 0 from the left, then we remove the absolute value and put a minus in front, right? Remember from algebra how you simplify absolute value expressions. Because if we're always plugging in a negative number for x, we're always below 0, then what's the absolute value then? What is this going to result in? Well, it's that negative times the negative, and you end up getting a positive number out here, right? And so from there, they can evaluate these one-sided limits by, this simplifies to 1 and minus 1, and then you get it's like kind of like a direct plug-in. It's everything this is just like the problems we've been working. You've got these rational expressions, the x's cancel. You're left with the y is equal to 1, y is equal to minus 1 constant functions. We don't care what's happening at the limit value itself, even though there's holes in these constant functions. And so there's the limit values, but they're not the same. So that's proof that, okay, well, in general, the limit as x approaches 0 of the absolute value of x over x doesn't exist. And this makes sense when you look at the graph, right? Yeah, coming from the left, it exists. Coming from the right of 0, it exists, but in general, it doesn't. Okay, this next example, we have the limit as x approaches 4 of this f of x here, this piecewise function. So when x is greater than 4, then it's the function square root of x minus 4. When x is less than 4, it's the function 8 minus 2x, but it's not defined at 4. All right, so this is a little bit different from the absolute value example, because if we're not going to do this graphically, then we wouldn't even really have the option to do a direct plug-in like we could have potentially done with the absolute value. I mean, we could kind of use direct plug-in and our intuition to figure out what this limit is, but I'm just saying that technically this function doesn't exist when x equals 4, right? So, but okay, we have the option to evaluate two one-sided limits here, though. The one-sided limit coming from above 4 will be based on the square root of x minus 4, and then coming from below 4, 8 minus 2x. And so that's what they do here. So we've got, with the properties we've learned so far, that those can be applied in both cases, because you can use that square root or nth root property here, and then just this you can do a direct plug-in here. And you get 0 coming from the left, or 0 coming from the right, and 0 coming from the left. And since both the left hand and the right hand limits exist and are equal, that means the limit as x approaches 4 in general of f of x is equal to that value, which in this case is 0. Okay, and just for reference, here's the graph of f of x. So you've got, here's the square root of x minus 4. There's the line 8 minus 2x. And so this is just continuous everywhere, but at x is equal to 4, there's a hole. The function doesn't exist. But that doesn't matter, right? When you're approaching 4 from both sides, you're approaching the same value, 0. Okay, this next example is based on the greatest integer function, so the greatest integer function, you input an x, and the output is the largest integer that is less than or equal to x. So this function always rounds down in all circumstances to give the greatest integer that is less than or equal to x. So always rounds down to the next greatest integer. This is also known as the floor function, and then the opposite of the floor function would be the ceiling function, which would round up in all circumstances. And so we can easily graph this function, right? It's this discontinuous function with all these jump discontinuities, but we can easily graph it because you're just going to have these straight lines at y is equal to the different integer values with on the straight lines, a closed circle at the end, the left end of each line, and an open circle at the right end of each line. Because when you get to 2 itself, then when x is equal to 2, the function, like once you've gotten not 1.999 trillion nines, exactly 2, the function doesn't evaluate to 1 anymore, right? It evaluates to 2. And then for any value, 2.1, 2.2, 2.3, etc., you're always just staying at, for any of those x values, you're just staying at the output being 2. Okay, well, a function like this is perfect for being analyzed with one-sided limits, right? So they want us to analyze the limit as x approaches 3 of this function, as x approaches 3 in general. Well, okay, what we're going to go ahead and do is, in this case, particularly with jump discontinuities like this, if you're doing a limit at a discontinuity value, go ahead and analyze the one-sided limits. So as x approaches 3 from the right, we can see that the function is going to be approaching 3, and as x approaches 3 from the left, the function is going to be approaching 2. So in general, since both one-sided limits they exist, but they're not the same, the limit in general doesn't exist as x approaches 3 of the ceiling or the floor function. Okay, but what about, let's think about what would the limit as x approaches 3.5, which would be 7/2 of the greatest integer function be? What would this be? Well, the function is continuous at x is equal to 3.5, right? You can draw this without picking up your pen off the page, going from 3 to 4. So the limit as x approaches 3.5 of the greatest integer function is just the function evaluated at 3.5, which is 3. All right, we could do this graphically. Coming from the left and coming from the right, you're just approaching the whatever the function is at 3.5. Okay, so now let's look at these next two properties. Theorem here says if f of x is less than or equal to g of x, when x is near a, except possibly at a, and the limits of f and g both exist as x approaches a, then the limit as x approaches a of f of x is less than or equal to the limit as x approaches a of g of x. Okay, so this theorem is pretty obvious, but from a rigorous math perspective, the textbook needs to state all theorems and properties like this. And so this is obvious because, think about it. If a function f of x is always less than or equal to a function g of x in the region around an x value a, but at the value of a itself is irrelevant. So like this is not saying anything about the functions having to be continuous. There's no restrictions at all, except that just near a, on both sides of a, for any x value you plug into these functions, these two functions, f of x and g of x, the outputs are such that f of x will always be less than or equal to g of x. Okay? And then with that, if the limit as x approaches a of both functions does exist, then it has to be the case that the limit as x approaches a of f of x is less than or equal to the limit as x approaches a of g of x. And this is obvious because the limits of the functions are going to have to be related to what the functions are evaluating to be whenever they're near a, right? Like, yes, what happens at a doesn't matter, but what does matter when it comes to limits is what the function is doing near a, right? If you're plugging the functions into your calculator, what are you seeing the outputs doing as you get closer and closer and closer and closer and closer to a? So what the function is evaluating to be near the limit value is what limits are all about. And so that's what they're saying here. They're giving us information about what the outputs of these functions are doing near a. And so that's what the limits of these functions are going as x approaches a are going to be based on. What these functions are doing near a. And so, well, if near a, the output of f of x is always less than or equal to g of x, well, then if the limits exist, the corresponding limit values are going to be based on those outputs. And so you can make this statement, right? How could it be possible that if f of x, the output of f of x, near a, on either side of a, is never greater than g of x, then how could it be possible that if the limits exist, that the limit of f of x would be greater than g of x? It wouldn't make any sense, okay? So now, next we have the squeeze theorem. And so with the squeeze theorem, we've got now three separate functions here. And same idea that when x is near a, but what happens at a doesn't matter, f of x is always less than or equal to g of x, which is always less than or equal to h of x. Okay, now if the limit as x approaches a of f of x is equal to the limit as x approaches a of h of x, so those two limits do exist, and they're equal to L, the same value, well, then it must be the case that if the limit as x approaches a of g of x exists, it's going to have to be equal to L. Okay, and they show this theorem graphically here, right? So the limit of g of x gets squeezed between h and f, and it's just based on this restriction here of the outputs of the functions. But most importantly, when this is the case when x is near a on both sides. And so now, but they show continuous functions here, right? But like the previous theorem, the squeeze theorem isn't restricted to continuous functions. It applies for any types of functions. And again, if that's confusing you, if you're wondering, well, how could this apply for functions with like jump discontinuities, perhaps like this, right? How could these theorems apply? Well, again, it's because of this restriction here on the relationship between the outputs of the functions when x is near a. You can't have like a jump discontinuity with a value of g of x jumping up here when x is near a, because then this wouldn't be honored. You see? But then also at the same time, another restriction on these properties is that this is only applicable if the limits exist. Like you have to have these don't apply if the limits don't both exist. And here, this doesn't apply if these outer limits don't exist, and then obviously if the inner limit doesn't exist. Okay, so now let's look at this last example. It says, show that the limit as x approaches 0 of x squared times sine of 1 over x is equal to 0. So the first thing we might think about is let's apply the product property where we can distribute the limit to each one of these expressions of x, right? So do this. Turn this into the limit as x approaches 0 of x squared times the limit as x approaches 0 of sine of 1 over x. But we can't do this because this limit doesn't exist. Why not? Well, okay, this is the 1 over x. So we want to think about, so we have the sine of 1 over x. Again, we'll learn later how, since limits are so flexible, we can bring the sine out of the limit. But if we just think about, okay, what is 1 over x doing as x approaches 0? Well, okay, this is one of those infinite limit problems that we talked about in the previous section. As x gets, since you're fixed at 1 here, well, as x gets closer to 0 coming from below 0, the function is going to balloon to negative infinity. Now, coming from above 0, the function is going to balloon to positive infinity. So the limit doesn't exist. But I mean, like, even if it was ballooning to the same infinity on both sides, so you could state that this was ballooning to infinity, well, it still doesn't exist. But then, like, the sine of that value, the sine of infinity is what? Well, the sine of infinity is just oscillating between 1 and minus 1. So there's no limit there. There's no like finite value. So this limit doesn't exist, which means we can't apply this property, the product property. Now, I want to note, though, and I probably should have made this more explicitly clear throughout the video, but like similar to the direct substitution property, the same idea applies with all the properties we've been talking about. So the property not being applicable in this case doesn't mean that, okay, well, since this limit doesn't exist and we can't apply the product property here where we distribute the limit, well, then that means that the whole limit doesn't exist then, right? No, that's not what they're saying. similar to what we talked about here, in that with the direct substitution property, if it's the case that you plug in the approaching value a into the rational expression and you're dividing by 0, well, that doesn't mean that, oh, well, then the limit doesn't exist. No, that just means you can't apply this property. That means you're going to have to do some other kind of analysis on the limit. And it's the same idea here with any of the properties we've been talking about. So we're looking at this product property. If it's the case that one of these limits doesn't exist, that's not saying that the limit itself doesn't exist. That's just saying you can't use this property to come to any conclusions. So we need to, if we come back, we can't make a statement about, like, we don't know that this might exist, this might not exist. We don't know. And the product, distributing this to this limit using that product property is not going to help us in this for this problem. Okay, and so what we do is instead we apply the squeeze theorem. And so we need to find a function f smaller than so yeah, to apply the squeeze theorem, the idea is we have this function here, and we want to look for a function that is smaller than this function. What they're calling this function g. So we want to look for a function that is smaller than this function, that'll be h, as well as a function larger than this function, that will be f, and then this will be g. In particular, the function f and h will be functions that we can find limits of. So to do this, we use our knowledge of the sign function. Because the sign of any number lies between -1 and 1, we can write that, yeah, absolutely, no matter what x is, unless x is 0, as long as you're in the domain of 1 over x, this is always going to evaluate to something between -1 and 1, right? Now, any inequality remains true when multiplied by a positive number. So yeah, with inequalities, remember, if you multiply all parts of the inequality by a negative number or divide, then you need to flip the inequalities. But if you multiply or divide everything by a positive number, then the inequality doesn't change. And so we know that x squared is greater than or equal to 0 for all x. And so multiplying each side of this inequality here by x squared, right? X squared is always positive or 0. So they multiply this entire inequality by x squared, and we get this. Okay, so look, there is g of x. There's the function we're analyzing, and we've got these two outer functions. And we can take the limits of these outer functions and use the properties of this section to evaluate these limits. And as x approaches 0, the limit of x squared is 0, and the limit of minus x squared is 0. And then also at the same time, we've got this inequality based on the functions themselves, right? No matter what, x squared times sine of 1 over x is always, for all x, less than or equal to x squared and greater than or equal to minus x squared. Now, I just want to point out, though, that it's not like to apply the squeeze theorem in general, you have to find a relationship like this that's true for all x. I mean, it's nice that that was the case here, but remember, if we come back, we just need to, this needs to be true when x is just around a. So remember, you have, it's more, there's more flexibility than this example we're looking at right here. They proved that this was true for all x, which is, that's nice, right? But you really only need to analyze the around the limit value itself. Okay, but since this is true for all x, and so one of all x, one is x is equal to 0, and these two limits are the same. Well, then the squeeze theorem says that this limit as x equals 0 of x squared times sine of 1 over x is equal to 0.